plus 3 plus 4.
Wait, that one says 4 at the top of does it start at 0?
Start at 0.
Because it's 0, he doesn't count it that.
Well, what about the 2?
Well, I'm adding, well, when this was 0 and this was 4, how many 2's am I adding together?
Oh, 5.
Yeah, it's just a logical implication. It's not like, there's no hard and fast rules for how you adjust these, right?
So the answer is not really, so the answer doesn't really change if the top was 5, if the top was 4 and I was 0.
Yeah, we are doing nothing to change the values.
Okay.
We're just making it easier to see what's going on in the summation.
Okay.
It takes a little bit of thought first, especially if you haven't seen summation notation before, really worked with it, then this is a little subtle right here, like trying to think through this.
It seems like going I and N represent an interval, and they always keep a certain distance. Even if you slide one, you have to slide the other one up, slide one down, and then slide the other one down. Is that
most of the time that's the way it works, but in this case, since the first value was nothing, I can adjust this
yeah, like,
willy-nilly.
yeah, if the first value is constant, that's obvious. But like, are we ever gonna give a scenario where we have to find make an area in a bigger triangle? Do you see what I mean? So we have to use something like that on a smaller scale. You know what I mean? Like we have like 5,000 rectangles, right? But they said find it from 1,000 to 2,000. What is the area between that? And then would we just change I and N to fit that?
Then you would seriously adjust the indices.
Yeah, those are just like it's like a scale, right? You can move it around.
Yeah, but you can't just adjust these pieces. It affects what's going on in here, except when this is constant.
Except when it's a constant.
That's correct. Yeah.
You just have to affect what's on the inside.
Right.
And so my last question.
Yeah.
How is the I portion 10 and not 5?
Because it's changing. Remember, the first one is when I is 1.
Yeah.
Then I'm adding. Then this goes up. Remember?
Okay.
It's always going up. So it goes to 2. So now I is 2. I'm adding 1 plus 2.
Okay,
Yeah.
Okay.
If it just been a 1 in here, then it would be 5.
Okay.
Or before. Sorry, before. If there was just a 1 in here or nothing in there, then it'd be 4.
Okay.
Yeah. Okay, do you want to do the left endpoint before we move on, or go ahead and do the right endpoint? The right endpoint is not that different. All you do is use right endpoints. You want to make sure you realize that this photo will change ever so slightly. That's the only thing that really happens. I'm going to keep that picture up there, and I will simply tell you what happens. When you use right endpoints, there's an important way to think about these problems. If you use right endpoints instead of left, then that means for the first rectangle, we would be selecting this value here to find the function value. That would give us this color. Use this cutting black here for a second.
What happened to the green one?
What happened to the what?
The green color?
I don't know. Thieves.
I'll go buy somewhere and just.
Right
You
here.
gonna buy me some? Good, you probably want to steal it.
Why would I steal it?
I don't know. You should buy green. I don't know. So, if you picked right endpoints and left endpoints, then your first rectangle would be here, and it would be an overestimate. What you should notice is that the first rectangle of the right endpoints is the second rectangle of the left endpoints.
Say that again.
The black is using right endpoints. Do you understand that much? You see that from the picture.
Okay.
Agreed?
Yeah.
I take of this subinterval, I'm taking the right-hand endpoint of that subinterval and going up to the function and declaring that height of rectangle. You got that, right?
Yeah.
You should notice that under the right endpoint scheme, the black scheme, the first rectangle area is exactly the same as the second rectangular area for the left endpoint scheme. And so forth all the way through the whole thing. So the third rectangle for left endpoint is exactly the same as the second rectangle for right endpoint. Agreed? There they are, right next to each other. Okay?
Yeah.
So what happened? What's the difference between a right endpoint and left endpoint ultimately? You have discarded the first small, it could be bigger in other cases. You've discarded this first blue rectangle. You're not using that in the right endpoint scheme.
It looks like you just slide everything.
That's exactly right. You're just sliding it down one. So what does that do? It kicks out this guy, he's gone, everything slides down, and now you have to introduce new rectangle you didn't have before. So all you're doing is exchanging a first rectangle for a last one. That's the way you want to look at it. So if that's the case, And down here in our formula, this was left endpoints. Again, Lee,
Sir.
you think you can figure this out? How is this formula going to change for right endpoints then? Give me what I just said about that geometric construction up there.
The n plus one.
You're
N
gonna
plus
f of
one.
x times the change of x plus 1.
I goes from 1
N plus
to
one.
n. Correct.
And
There it is.
just N.
It's all changes.
I like,
Like what better?
I said I like the right.
Yeah, it is better. Why is it better? Because now it all starts at 1, right? All the summations start at 1, which conforms to the normal way you think about your 3 formulas I showed you. So when you have the option, you should probably use right endpoints. Right?
You could leave
So like-
you could leave that I at 0 and just put n plus 1 if you wanted to, right? 'Cause you're just
No, that would give you that first small rectangle you're kicking out. That would give you this one as well. You'd be computing this one like off to the side here.
oh okay.
And then you'd also be introducing this one, so it's giving you a gross overestimate,
Oh, okay.
because it's not even underneath the curve at that point. Yeah.
So when you give us a problem like this, are we gonna have the option to choose either one, or are we gonna do the?
It'll say. Like this one says to do both, so now we'll do a right endpoint. We'll do exactly what the black drawing has now, right? That's what we're gonna do, okay? So we do a right endpoint estimation, then it should be an overestimate, a complete overestimate, because every rectangle is above the curve now, right? So the computation is remarkably similar, but the formula just slightly changed. So let's see, what was that? So we'll have, we'll circle what's left in. Okay, so we'll have i's going from 1 to 4, no, 5 in this case, right? It is 5, sorry, 1 to 5. And the function's the same, right? It's still x plus 1. But what am I putting in here? Putting the exact same thing, a plus I delta x. A is still 1, right? So everything looks the same so far except for these two things. That's all it is. So I should have, whatever it was, 1 plus I plus 1 was I plus 2, right? Ultimately, it's I plus 2 sitting in here. The delta x is exactly the same. We didn't change that in this problem. Okay? So here's our formula now. So if we run the summation notation through here, again, computationally similar, but has different indices. 5, and then equals 1, 2, 5. So how many 2's am I adding up this time?
Five.
5. 10. Right, 10 of them. So this is still 10, agreed? Why is that the same? If you think about it, all that really is this. It's the rectangular underside of this thing. Right? Here's 2, right? Area 2. 2 by 1. 2, 2, 2, 2, 2. That's 5 2's. That's what that part of the summation is computing. You see that? Okay. So that's why I stayed the same between both problems. And now what's happening? This part is computing what? That's right. An extra piece here. A minute ago, the first one, when it went from 0 to 5, what did it go through? It was 0 to what?
0 to 5.